Hello everyone, my name is Utku Culha and I'm a postdoctoral researcher at the Max Planck Institute for Intelligent Systems in Stuttgart, Germany. Today I'm going to talk to you about my research on soft robots and physical intelligence, and I will give you examples about how this research might change our current and future lives. So let's begin. We humans have been building our systems with a method called the top-down design strategy. In this strategy, we have a really clear idea about how the final product will look like. So we bring other elements and systems together and we assemble them and build this final product. Of course, this method has given us amazing tools and machines and systems that took us to outer space. Just like these systems, we built our robots in the same way. We use the top-down design strategy and, importantly, rigid materials to build robots that can work in heavy-duty operations like in this car manufacturing business. Of course, the robots are really precise and they never get tired or complain, but if you think about it, they're quite different from the creatures in nature. The living beings in nature are made of soft materials and they really don't emerge out of a already known design. They actually emerge from the collective behavior of simple and soft elements and their interaction, which gives them this amazing physical adaptation capabilities. So the question becomes, how are we going to build our robots like them? So one thing is for sure, we should use soft materials, but the question also becomes, are we also going to make them look like animals, but also make them behave and adapt like these animals, showing physical adaptation capabilities? So this question pushed the definition of intelligence in the recent years. Originally, the intelligence was focused around computational intelligence, such as the more brain you had, the more intelligent you were. But in the physical intelligence definition, the brain and body are co-developed and they're equally important in defining your intelligent behavior. So following this discussion, a good question comes such as why the trees don't have any brains, and the discussion follows because the trees don't have to move around. If you move around, eventually you will bump into other complex mechanisms and systems, so that you will have to have an adaptive body and a brain accordingly. So actually, unlike the trees, if you think about our organs in our body, for example, our hands, eyes, or tongue, which are the organs that interact with the most complex environments and stimuli, they cover the largest part in our brain, and this is what this statue is representing. This is a good example of how the physical intelligence takes place and the co-development of brain and body, but at the same time, the material properties of the body is really important. If you think about it, our bodies and all the living beings are made of soft and deformable materials that are physically compliant and self-healing, which gives them this physical adaptation property. So once these materials are adapting to the environment passively, you use your brain to focus on other important things. But unlike these, we have been using rigid materials in our machines and systems because we wanted them to endure heavy-duty operations. But once we tried to optimize them in that sense, we lost their physical adaptation capabilities. So I was very interested in this line of research, so I started using soft materials in my robots, and human hands were one of the best examples to begin with because that was a good combination of soft and rigid materials, and as a machine it was showing impressive precision, dexterity, adaptivity, and flexibility. So I took the human hand as a guide of the design and I started building robots in that way. So I brought human bones. They were not actually human bones, they looked like human bones and they were rigid, and I assembled these bones together. Unlike the conventional robots where you have rigid joints, I assembled them by using soft and deformable materials that represent tendons and muscles. So eventually we built this creepy looking robotic finger, which had a hybrid combination of soft and rigid materials. So this balance of materials gave the robotic hand a balance between exerting forces to objects, but at the same time physical adaptation capabilities to comply with the objects that it manipulates. So with this robotic hand, now we were able to manipulate a different range of objects, such as food. Food is quite diverse in its stiffness, thinking about, for example, the bread, eggs, lettuce, or carrots. Now we were able to manipulate these objects, and not only this, we were able to use our robotic hands in the agriculture and food making process, but at the same time, we could use them in supply chain operations because we were able to handle rigid objects such as picking up objects from the shelves in a market or a warehouse. Of course, using soft materials enabled us new application avenues, but soft materials come with a challenge because soft materials are really deformable, and once you start to think about the robot motion control issue, the robots will not be able to respond to the conventional control methods because they move too much. And this becomes a bigger problem once you start building robots on a small scale. So to address this problem, we built this robot you see here, which is approximately 4 millimeters in length. It's an elastic material which has embedded magnets inside it, such that once you apply an external magnetic field, this robot deforms and moves around. So we wanted this robot to walk like a caterpillar, but we didn't know how. So we took this robot and then we placed it inside this nuclear reactor looking machine, which is actually electromagnetic coils that converts the electric current into magnetic field. So we used the machine learning system and told the system that we want this robot to walk like a caterpillar, but we don't know how, so you should solve it. So this machine learning system tracked the robot all the time, tried out different magnetic fields, directions, and orientations, and it started from dancing around, and eventually it managed to find this correct controller parameters that got the robot move like a caterpillar that we wanted. So you can now think about, yeah, maybe these machines can start learning other things that may not be as peaceful as making a robot walk, but at this point, I think we're still very far from away from that, because we can just simply unplug these systems. But instead, now we're using machine learning systems and soft materials to build robots and explore new designs and functions that were actually unknown to us. So in a sense, now we are co-developing humans and robots at the same time, such that we build robots that are physically adaptive, that can make our lives much more easier and hopefully much more entertaining. So thank you very much.